Now we come towards the next question. We have to find the time period of the spring mass system. All the laws will be the same as we are discussing earlier. Whenever we take a case of spring and spring is stretched, it can be vertical displacement or it can be horizontal displacement. But every time the restoring force is directly proportional to displacement. And this is normally written as F is equal to minus Ky. But if we wanted to find the magnitude, we have to take the modulus of the number. So F is equal to Ky, and K stands for spring constant, which is F over Y. From this, we have to find the time period of the spring, and the mass is m. So time period is calculated by formula 2 pi under root m over k. Now let us come to the main context. So figure is indicated here. That is, one of these spring is with constant k. Other spring is indicated with k. Mass is m. And two other springs are connected in series, and each have a value of spring constant 2k and 2k. So k is connected to 2k and 2k in parallels. But the whole, that is the total result will be in the series combination. That is, first of all, k and 2k will be estimated, then it is added to k. This is what our question. Now we have to start with the solution. So what we are finding, that is k spring constant is 4. That is for series combination. So we can just see that for 4 when we write, it is a spring constant of the combination of springs. Then there are two other springs, and that is one of them is 1, the other is 2 and 3. So 3 is having force constant 2k and 2 also having the force constant 2k, and k has force constant 1. So total force constant will become 4k. Now, effective constant of the spring 2 and 3 will be k dash. Now this is to be applied in the series combination. It is 1 over k dash is equal to 1 over 2k plus 1 over 2k, and if we evaluate the number, 1 over k dash will become 2 over 2k and 2 will cancel off. So 1 over k dash will be equal to 1 over k and k dash will be k. The same figure is shown here. Again, the series and parallel combination of the springs in the given figure. So effective constant of the spring 1 and 5, that will be k double dash, and k double dash will be addition of k and k, which is again 2k. Now, this is shown, that is the resultant combination as shown above. Now this is the combination. We have simplified the combination. So effective constant of spring 4 and 6 will be k triple dash. K triple dash will be k plus 2k, and the net result will become 3k. So time period is 2 pi under root m over triple k, and for triple k we have got the value, triple k has got the value 3k. So it should be t is equal to 2 pi under root m over, and this is triple k. Triple k can be replaced by 3k. So final equation will become t is equal to 2 pi under root m over 3k. Now our next question is that periodic time of oscillation. Periodic time of oscillation means that whatever particle is moving, it is maintaining the periodic motion, and the motion is repeated after regular intervals of time in to and fro direction, but the motion is unidirectional. So periodic time of the oscillation is T1. It is obtained when mass is suspended from spring. If another spring is used with the same mass, so it means mass is not changing, but the springs are changing. So obviously the constants will be K1 and K2 in this case, but M remains same. Then periodic time of oscillation is T2. So earlier it was T1 and now finally it is T2. Now if this mass is suspended from the series combination of above springs, then time period will be how much? So what we have done, we have taken T as 2 pi m over K1 because there are two springs but mass is same, and we square the number. So one of the time period will become T1. So T1 square will be 4 pi square m over K1. And from this equation, we get the value of K1. Similarly, T2, that is taken as 2 pi under root m over K2. This is the second spring. And from this, we get the value of K2 by squaring. And now, finally, we will write time period as 2 pi under root m over k dash, because the value is given to us k1 as 4 pi square m over t1 square and k2 as 4 pi square m over t2 square. If we divide the two values, we find we will get k1 over k2, and that will be 4 pi m square. 4 pi square m will cancel off, and we will get t2 square over t1 square. Then we finally compute the value, and the final result will come t is equal to 2 pi under root m over k dash. This is shown in the figure. Now we are again taking the figure. There are two springs. Force constants are K1 and K2. The masses are same. So 1 over K dash is 1 over K dash plus 1 over K2. The value of K dash we have to calculate. So that will become K1 K2 divided by K1 plus K2. This is simple algebra we have used. Now we compute the values of K1, K2. Then in the numerator, K1 and K2 are multiplied. So we have written 4 pi square m over T1 square into, that is a dot. Dot means multiplication. It is 4 pi square m over T2 square whole divided by 4 pi square m over T1 square plus 4 pi square m over T2 square. Now from the denominator, we take out common as 4 pi square m, and the remaining result will become 1 over t square plus 1 over t2 square. Then we take the LCM, and then we make the cancellation algebraically. So the final result, k dash, we have computed the values as I have suggested earlier. Then we get the value of k dash, and our final result will become k dash is equal to 4 pi square m over t1 square plus t2 square. Now, t is known to us, 2 pi under root m over k dash, 2 pi m over, now m over k. So the value of k we will compute, that is we have calculated 4 pi square m over t1 square plus t2 square. So by computing this value, 2 pi will cancel off, and our net result will become t is equal to under root t1 square plus t2 square. That is the final value. Now, in the another question, there are infinite spring. Infinite spring with force constants k, 2k, 4k, 8k respectively. What exactly is our observation that these numbers k, 2k, 4k, etc., if we take out k as common number, then 1, 2, 4, 8 will be a sequence, that is a geometric sequence. So what is our question? There are infinite number of springs. So infinite spring with force constants k, 2k, 4k, 8k respectively are connected in series. The effective force constant of the spring will be how much? That is, we wanted to find the resultant force constant. So to solve this question, 1 over k effective is 1 over k plus 1 over 2k plus 1 over 4k plus 1 over 8k plus so on up to infinity. Now what we find is that k is taken out common. So 1 over k is common. So 1 over k effective will be 1 over k into 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 and so on. Now we find that 1 plus 1 by 2 plus 1 by 4, 1 by 8 is a geometric series up to infinity. We know that sum to infinity is calculated by a over r minus 1 if r is greater than 1. But if r is less than 1, then sum to infinity will be a over 1 minus r. This we read in geometric sequence in the mathematics of 11th class. So, A is the first term, R is the common ratio, and we are finding that common ratio is less than 1. So we are using a formula. S infinity is A over 1 minus R. By using this formula, first term will be 1. Ratio will be 1 over 2 divided by 1, and that is 1 by 2. So after calculation, our number will become 1 over k within the bracket 1 over 1 minus half. Half we have computed for R. We have calculated the value, that is 2 over k. So k effective will be k over 2. We will inverse the function.